Since we've got lots going on, we better go ahead and get started and at least do as much as we can. As we've done with every unit in this course, we've got a few weeks to kind of introduce you and get you acquainted and familiar with kind of this new stuff and see where that takes us. And so that's what we want to do here with this last unit on modern physics, because there's obviously a lot to teach you. And of course, I got to keep remember it's just that. It's an introduction. You've got many more semesters of your education that you are going to get. And so keeping with that theme, you guys will notice that I set out the tests, and hopefully you got a chance to pick them up. But I don't know if you saw that the solutions were here. And so some of you got them, some of them did not. You're looking at it like, did you want to copy? But I've got the solutions listed out there. And so scan through that. This will probably answer a few questions, but probably not all of them. And particularly that the way it came out was kind of interesting, because I thought, what would be a hard one, and it was fairly hard, was the one that was tilted in. That was the one that I thought would be the hardest, and but it actually wasn't the hardest. I think the first one turned out to be the hardest for most people. It was just some geometry there. So take some look at those. But that one surprised me that it was the hardest one by far there. And there were some other ones that I thought might be a little bit hard that you guys nailed, and I forget which it was right now.
The fish may have turned red.
Oh yeah, the color of the fish. Yeah, that was kind of a mixed one there. I thought that would be a no-brainer too. The first question said block the gold light, so what's left was nothing, and it should be black. So and fortunately, a lot of you saw that right away. Others of you calculated it out and found out that there was nothing in the visible spectrum, and then said it was black. Well, that was good. You said it was black after a lot of calculations, but yeah, there was nothing in the visible spectrum. But keeping with that theme, like I said, let me just pass those out. Let's see how time goes for you, and see what kind of questions you have. Meanwhile, let's keep going with our modern physics so that I can get you acquainted with as much as possible. And so I'm going to start with the idea that might be a bit shocking to many of you. This was that time dilation. And so let me make sure I get this clear in your mind. Here's what we came up with. We went through a long analysis to show that if the time is the same for two observers, which was a process that we had assumed in all of our physics up until this chapter, then our speeds would be different by different observers. Meaning that if I was traveling in a spaceship at half the speed of light, and I were to shine a laser beam forward and watch it go at half the speed of light, you would see a speed greater than the speed of light. You would see a speed that would be 1.5 times the speed of light. That's how it would work if the time was the same for every observer. And that's what we had assumed up until we got to this point. And it was Einstein, as I mentioned, both his brilliance and his boldness to say, perhaps that's not the case. Because experiments at that time were clearly showing that when somebody is moving along and shines a laser beam, that person will see it moving at the speed of light, and every other observer will see it at the speed of light. Which I know sounds very surprising at first, but the only way that can work is if time is different for different observers. And that was the main point. And so we called this time dilation. We put in here proper time, and what we said is moving clocks run slow. And so we learned then that the flow of time, and that's a good model, picture this. It's a flow of time. Imagine yourself on a river. This is a river of time. and this river can fork into different directions, and some people can flow at a different rate of time, and that's how we got into that twin paradox. It is the consequence of time being different that really is the foundation of everything we've done in mechanics. Because everything we've done, kinetic energy, momentum, conservation of momentum, velocities, accelerations, forces, F equals ma, all of this assumed the time is the same for each observer. So what we have to relearn is all of our mechanics. We got to start again. Everything we've been doing gets readjusted. Now, of course, as we pointed out, it gets readjusted by this gamma factor. This gamma factor is essentially 1 when we are less than 10% the speed of light. That's why the world we live in is going slow, and we're used to thinking of time being the same for each observer. But once you end up with accepting time dilation, the first consequence of that was what we came across and called a length contraction. And so the proper length divided by gamma becomes the length observed by the observer here. And so what we said is moving objects shrink. And so we have our length contraction. And the point we learned last time is that both space and time are not absolutes. They are dependent on motion. They change. And what we think of a certain time and what we think of a certain length does vary. And so what we like to do is we like to, and I guess I'll change colors here, we like to take this old notion of space and time and replace it with space-time, and said they are connected. And I tried to leave you last Thursday with a little picture, if you will, of how an object moving on the x-axis and the y-axis would be the equivalent of an object moving in space and time, and when one changes, the other is affected. And so the best answer I can give you is we do not live in a three-dimensional world, x, y, and z, and time. We live in a four-dimensional world, x, y, z, and time. We have all of those interconnected. And changing one affects the other. And so for the rest of the chapter, we are going to look at additional consequences of the fact that the time is different for each observer. And so let's re-look at some I shouldn't say re-look at the consequences, but let's re-look at some of the things we've been doing back in Physics 121 and reapproach them now with time being different for different observers. And we'll start with this first one. How about adding, and I'll put it in quotes, speeds. Now, let's just have a discussion here for about 20 minutes and say, let's do this. You're going to be the first observer. Let's just say you're sitting in the classroom or you're sitting on a park bench and you're just sitting there. We'll say you're not moving. I'll be the second observer. I'll be on my bike going down the bike path at this park. So you're sitting on the bench of the park. I'm riding my bike. Each of us look up at a bird flying. If I was drawing a picture, it might look something like this. Here is a bird. Good drawing, I know. But here's my bird. When you go through the reading, you'll see that your author just calls it the point P, what he says, the event. So we're going to watch something here. Let's watch this bird. Now, who's going to watch it? Well, both of us are going to watch it. So let's say this is the system S, U. So S for system. You are going to measure this bird. You would be looking at an x-axis and a y-axis. Now, to keep it simple, let's just say the bird is moving along the x-axis here. So you look up and you see the bird moving and you say, you know, that bird is moving with a speed of 20 miles an hour. Okay, that's what you perceive. But I'm on my bike and I'm cruising along my bike. A pretty fast pedal, I'm going 15 miles an hour. And I look up and see the bird. Do I see the bird going at 20? No, what do I see? 5, right? From my perspective, you would say it is 5. And what you did is you just subtracted them. You also assumed the time was the same for both of us. And so in what I would call the old theory, the Newtonian or classical physics, it really is just adding and subtracting to find out the speeds. It doesn't quite work that simple, does it? So let's re-ask the question. What would the speed that I would see? Would I really see only 5? Now, since our speeds are kind of slow, I would say, if it's not exactly 5, it's pretty darn close to 5. But this could change dramatically if we're getting close to the speed of light. And so that's why I want to reanalyze this. And so let's reanalyze it. The logic is relatively straightforward. It does take some careful thought on the notation, and that's probably the hardest part of this part of the chapter is the notation. So let me say it again. You are the system S. You represent the position of that bird with X and Y. The reason I say that is because there'll be another system watching the bird, which will be me. So distinguish my reference point from your reference point, I'm going to put a little prime on there. Okay? That means I would measure the position of the bird X prime and Y prime. And so let me make sure I got this clear. There's 2 systems here. There's a coordinate system measured by you. Those would be the X and Y without the primes. There would be a coordinate system measured by me. Those are with the primes. You and I are moving relative to each other. So we will say then that this coordinate system is moving this way with a velocity of v. V for velocity. Here's where the notation, I think, needs some clarification. Because v is not the velocity of the bird. You got that? V is the velocity that I am moving relative to you. So if you look at the bird, we need a symbol for the speed of the bird that is not a v. Fair enough? And so that's why your author says, let's say this object then is moving with a velocity of u, just to make sure it's clear. And likewise, I would look at the bird. I would see a speed for the bird. My speed that I see the bird moving is different than the speed you see it moving. Fair enough? And so let's call that u prime. And so let me begin here by making real clear on the notation, because I have noticed in the past that once students figure out the notation, then they can just put in the equations and solve. That's not the real problem. The real problem is, what do each of these mean? So here is one observer, here is another observer. One observer is listed in terms of X and Y. That observer would see the second observer moving with a speed v. They would see the object or the event moving with a speed u. Fair enough? The moving observer, actually they both could be moving, but the other observer, the observer from the prime system, would measure the location of this object in the X prime and Y prime. And maybe I should have put this. So point P can be either labeled as XY or X prime, Y prime. And so these 2 different people are measuring 2 different locations based upon their coordinate system. And the 2 coordinate systems are moving relative to each other. That's what the velocity v is. Which is why then, when they look at the object, well, we'll just say it's a bird, that one person, which I'll call you guys measuring from the S system would say the bird is moving with a speed u, and me, riding my bike, measuring from the S prime system would say that the bird is moving with a U prime. Fair enough? So a lot of notations there, okay, but two different coordinate systems. So we have prime and unprimes. And the big one is the V is not the velocity of the bird. The V is the velocity between the two observers. Fair enough? The U is the speed of the event. So that's why we have a U and a U prime. Okay, so let's do this for a moment. To make our discussion kind of easy, let's do this. Let's say you and I are at the same location at time equals to 0. And so we kind of pass each other, our origins line up. Meaning that at some later moment in time, you would look at me and say, well, where am I? Well, you would say, well, he's moving with a velocity v on his bike. He's been doing it for 3 seconds. He must be that far ahead of me, right? And so as time would evolve, this position would get further away, right? And so that's what you would say my position is. Because here's kind of my question for you. If I were to look up at that bird and say, what is the position of the bird as seen by me? But you're asking the question. How would you figure out what the distance is for me? Yeah, wouldn't you look at your coordinate system and you go, well, how far over is the bird minus how far over is the rider? That would be the distance. Fair enough? So you would say, okay, I see the bird, say 100 feet, minus the bike rider, who's now, say, 75 feet. You would be saying, all right, that bike rider must be saying that the position of the bird is 25 feet. Fair enough? With one subtlety. The size of my 1 foot is not the same in each reference frame. And there's the catch, right? They would look compressed. You would look over at my coordinate system that is measuring the bird, and you would say, well, if his coordinate system had been the right size, this is what he would have gotten. But his coordinate system isn't the right size. In other words, this representing one, and I shouldn't have used feet, I should have used meters. So if this is meters, then you would look over here and you would look at the little markings on my grid and you'd go, they're closer together. Now, if you didn't understand modern physics, you would think, that's just painted wrong. Somebody built the meter sticks too short. But now that you know modern physics a little bit better, you would say, this would have been the number that we would have counted if they had been this size. But instead, they are crunched together, so there are more of them. How many more of them are there? Well, that's what the factor gamma was all about, right? They got crunched together by this factor of gamma. And so that's what you would have said. Yeah.
This is what, sorry. Would you look at your own feet measurements and they would look normal to you? They wouldn't look compressed.
Oh, right, mine wouldn't, yeah.
Or when you're on the bike, S prime.
Oh, yeah, good point. And we're going to do the reverse of that. Just a second here. Yes, yes. I'll say yes and then do it here.
When you look at ours,
right.
Do ours appear longer or shorter?
Shorter also. Okay. And again, at first that might sound like, well, wait a minute. But again, if the picture I left with you on Thursday helps, here's 2 rods, if you will. I would say they are the same length. But if I rotate them, and for simplicity, I'll say I just rotate them in xy instead of rotating them in xt. But if this person looks at this one, it says this one is moving relative to this one. That's like a rotation. And so as this person looks back at this one twisted, if there was a shadow on the wall, it actually occupies less on the x-axis because it's rotated. Now in this case it's rotated in the y, but what I'm trying to illustrate, it would be rotated in time. So in terms of space, I wouldn't see that. So when I look at this and I say this person's moving, that's like a rotation, then from this guy I look back, that's shorter. But that's kind of what this person sees. This person looks back and sees this one rotated and says, no, that one's shorter. So maybe when viewed that way, the dilemma goes away. It almost sounds counterproductive, like, wait a minute, that's shorter, who's shorter? They're both shorter. Okay? They're both a projection into the x-axis as they see it. Which is the next step I want to do, unless you had the question.
Yeah, just quick. This X prime that we just wrote is I would say about the biker's distance on the bird.
Right. So notice these in here have no primes. So these are numbers you would measure. You would measure what's the distance to the bird at a particular moment in time. You would then get out your calculator and calculate the value that the bike rider would say the distance is. Fair enough? So that's what I mean by the x prime. The reverse works just as well. What would I measure and then use that to calculate what you see? So as I am riding my bike, I would look up and I would see the bird a distance from me, x prime. And then I might ask, well, I wonder how far you guys think the bird is from you. So what I would do is I would take, well, the bird is so far in front of me, but I'm this far in front of that observer. So I would add to it the distance that I feel I'm in front of you. And so instead of subtracting, I would add. And that's the same way we would have done before we got started in our modern physics. The only thing that changes, though, is that as I am riding my bike and I look back, I notice that your coordinate system is shrunk. And if your meters were the same as my meters, then I would have said this is how far you measured, but your meters are smaller than my meters. So the number you get is bigger by a factor of gamma. And so this is our first step in relativity. How would I measure the position? How would you measure the position?
Are those factors of gamma are different for this, right?
No. Now, the nice thing about this, the factor of gamma is not different, because if you remember the train one we did with the length contraction, the speed that you see me moving is the same, right, as I see. So the v, and notice I didn't put a v prime here because the v and the v prime are the same. And so the gamma is the same and the v's are the same. So that makes it a little bit easier. If there's going to be anything nice to talk about the e's, that's one of them, is that, okay, the speeds are the same. So time and distances aren't the same, but speeds are. And so that's really kind of the real key here, is to realize that the things that seem to be the same between the reference point is velocities, not time and not length. And certainly not position, as we will soon see. And so there would be the mathematical connection. Now, if you're willing to accept that, the rest of these go pretty easy. Vertical direction, we kind of touched on it in passing. Somebody asked a question, I can't remember if it was this class or the next class, but the contraction is in the direction of movement. So there is no contraction vertically. And so that's the same. And I guess it works this way. So that if I measured the bird being so far up in height, which I would call that y prime, you would measure the same thing. There's no motion in that direction, so there's no compression, and so the vertical one doesn't change. We could put a z on there also, but it's hard enough, so we'll just do xy plane. All right. But what about time? See, what time would I have on my watch compared to your watch? Now remember, we set them at 0 at the same moment, right? Back here? That was kind of our discussion here, that we would be at the same position at time equal to 0. So when we cross each other, we have the same position, 0, 0, at time 0. So we each start our watch. But as I move forward, my watch runs at a different speed than yours. So if I were to ask, what time do you have on your watch? But I have to get that information from my watch. I would look down and say, okay, I have t prime. I also have the velocity I'm moving. From that, could I get your time? And I could, but we're going to save a little bit of algebra. Or we're going to skip a little bit of algebra to save some time. It was Einstein who put this together here and said, well, look carefully at this. Isn't this a perfect recipe? What if I put that into here? If I were to put that first equation, which says x prime equals, then I have my gamma, and in place of t, I could put x prime plus vt prime gamma. So there's putting x into here. Let me not forget to subtract the vt. And if you look closely at this equation, you can see there's going to be a lot of algebra. But don't we have things like x prime, gammas, x prime, t prime, and t? So couldn't we go through a lot of math and find t equals what? The time on your clock. I could get by measuring my position and my clock. Fair enough? And so I'm going to save myself and you some algebra here and give an answer. And I feel a little guilty for doing that, but I think it's best in what we've got to do. No? Oh, good. All right. But if you got some time, go through some algebra here. This is what you will get. And so this is how I would measure time and my position. X prime, I'm sorry, bird's position. If I got this right. Then that is the time you would see. I could do the reverse of this, right? I could put this equation here, x equals gamma, and in place of x prime, I could put gamma times x minus vt for x, and then plus vt prime. But I'm hoping if you look at this, you'll see that it's kind of like this equation, where I can solve this for t prime. I could say, what would you say my clock reads? Based upon what position is the bird and what time is on your clock. And you can see that the symmetry in the math makes it come out with the same thing except for with a minus sign. And so this would be our first, what I'll call transformation, if you will, by saying what position would I get? What position would you get? How are they connected? Our x's. What time would I get? What time would you get? And so that's probably the easiest one. I haven't even measured the speed yet I see of the birds. That's coming up next. But this is our first relativity calculation. What position do I see based on your information and vice versa? Yeah.
So what is c?
C is the speed of light.
Okay, c.
And yeah, and it looks a little funny coming out of nowhere, but remember there is a c in the gamma function. And so after you do some algebra, it shows up. Yeah. All right, well, let me keep going, because this isn't quite what I was after, although this is going to be very useful. It is going to, again, say, what distances and positions do I measure compared to you? But what I really wanted to ask you was right here. What speed is the bird moving as seen by me compared to the speed seen by you? And so if I may, it's going to take a little more algebra and calculus here. I'm going to go ahead and erase this. But don't forget what those symbols were that I tried to make very clear, because I'm going to use that information and I'm going to ask this. U prime is really what I'm after. I'm really after what speed do I see the bird? Right? Remember, you're sitting there on the park bench. I'm riding my bike at 15 miles an hour. You see the bird moving at 20 miles an hour. What do I see? Do I see 5? Not quite, but pretty close. I know that if our times were the same, I would see 5. And I know that at these low speeds, they pretty much are the same. So whatever formula I get should be different than just the simple subtraction, but not that much different at low speeds. Fair enough? So let's give it a try here. And we can write this as the derivative of how the position changes divided by the time changing. And so if we come over here and we say, let's take the differential of the dx. So the gamma doesn't change because that's the speed I am moving. But what would be changing is the position as seen by you of the bird and the time as seen by you. Oh, minus sign. Sorry. Minus sign. Get my symbol straight there. And likewise, that's why I needed the second piece of the equation. How much time would elapse as seen by me? Well, that would be another factor of gamma. And then I would have a dt, and then a minus v dx. Thank you. dx over c squared. And I'll go ahead and then multiply top and bottom by, say, 1 over dt. 1 over dt. So what happens in the numerator, notice the gamma factors go away, but what I get here is dx dt for the first term minus v over. Well, let me stop right there. What would you have called dx dt? That's u, right? That's the speed of the bird. Not v, right? But u. I think you guys got the right idea. It's the speed of the bird, which the symbol we are using for the speed of the bird is u. So it's u minus v. Now, if that's all there wasn't this other stuff down below. This, I think, makes sense. Isn't that what we would have said in the simple case if we were back to classical physics? We would have said, look, you see the bird going at 20 miles an hour. I am moving at 15. 20 minus 15 is 5. And so the numerator is our old classical idea. The extra stuff is down below. And so we are going to see what? Well, here is a, well, I'll put it here, is a 1 over dt. That is a 1 minus v. And what would this be? dx dt. That's the u over c squared. And I guess there's no real change I need to make. And so there is what I was after. The new addition velocity formula. How would I see the speed of the bird? Now, if I was actually doing this calculation for such small speeds that we were mentioning, it's kind of pointless because the speed of my bike times the speed of the bird divided by speed of light squared is really small. And therefore, I really just have a 1 downstairs, and that's what we're pretty much useless to. This would, I guess, look something like this. I kept saying miles per hour. Can I just change it to meters per second? So I'm putting some numbers here. But if it was 20 meters per second minus 15 meters per second. Oh, I wish I could ride my bike that fast. I have a hard time keeping it 15 miles an hour. But then this becomes 15. And the bird was 20. And the speed of light is that. And again, that number is so incredibly small that I don't think I can even get it on the 10 decimal places on my calculator. In fact, I know I can. It's 16 decimal places there. So 15 times 20 divided by 3 exponent 8 squared comes out to be 3.33 times 10 to the negative 15. That's 5. So in terms of these low speeds, they do match what we would have thought and what physics and scientists and engineers all work with, at least until 1905 when Einstein kind of published all these results here. And so you come up with a 5 because this is just too small to be noticeable or measured, because again, there's always a partner who's going to make a little mistake along the way, and so you don't come up with exactly 5, you just think your partner made a mistake along the way. You don't really think it was something new or different. However, let's change this. Maybe a little unrealistic, but let's say I'm riding my bike at half the speed of light. And you look up and see the bird flying. Oh yeah, why not 3/4? Why not 3/4 the speed of light? I think your reaction might be, well, what do I see? Well, if the bird's going 3/4 the speed of light and I'm going half the speed of light, I think your reaction would be, I must be seeing it going in 1/4 of the speed of light, right? No. It won't work that way. Let's give it a try. What do I see? Well, let's come back to here. Let's see. The bird is going 3/4 the speed of light. I'm riding at half the speed of light. If the denominator was not here, I would get 1/4 of the speed of light. That's what the numerator was doing, the old classical physics without the time dilation and length contraction. But when I put this in here, then I get a 1 minus, and for my speed it is half the speed of light. The bird's speed is 3/4 the speed of light. As I put those in, I get 1 minus, looks like speed of light cancels off, and I get 3/8, which then is 1/4 over 5/8. which is what? 1/4, 8/5, c, which is what? 8, 2/5. 2/5 the speed of light. So 2/5 the speed of light is 0.4 c, where kind of would have expected it to be that. Interesting. Or let me put it another way. I think it's more enlightening the other direction. What speed do I see? I'm riding along. I'm riding at half the speed of light. I look up. I see the bird moving at 0.4 the speed of light. You might have thought, as you look at me going half the speed of light, and I see the bird going at 0.4 the speed of light, I bet your reaction was the bird should be going 0.9 the speed of light. But that's not what we have. The bird is not going 0.9. The bird is going 0.75. They're not just simply additions and subtractions. Unfortunately, that's gone, and we have something more complex. Here's my favorite one. What if, again, I'm riding my bike at half the speed of light, or forget any speed. Let's just say it is speed v. This could be a small speed, this could be a large speed, just speed v. And I shine a flashlight. What speed do I see if you see the flashlight going at the speed of light? Shouldn't it be the speed of light? I mean, wasn't that the whole beginning premise here? That we started this whole idea saying that both observers? So does it work? Let's give it a try here. All right. So what speed do I see when I'm riding my bike at any speed? Well, you look up and you see the event, the bird, going the speed of light. I'm riding my bike at some speed v. This could be half the speed of light. This could be 1/4 the speed of light. This could be any speed you want. But what's nice about it is watch what happens downstairs here. My speed here is v. The speed you see from the flashlight is c. And I get that c squared. Now I guess one of the c's cancel off. And in fact, downstairs, I would have a common denominator of c. And so I'd get c minus v. That becomes, when we flip it and cancel, what speed do I see? I see the speed of light, c, also. And so both of us see the light traveling at the speed of light, regardless of what speed the bike is moving. Isn't that brilliant? Right. And so it does work. Everybody is going to see a beam of light traveling with the speed c. If one person, any person, sees it at c, everybody would see it at c as we add it together.
Both of them are at the speed of light.
Both of what are the speed of light?
Both of me and the bird is speed of light.
Oh, so I'm going the speed of light. Well, back here, I guess I would have 0/0, which is the speed of light. And I'll just say it that way. But I guess we would see it at the speed of light. So a light beam shooting a light beam would then be observed by somebody seeing it a light beam. Yeah. And we would have to take the limits here and do some L'Hopital rule stuff, limitations. Fair enough?
Wouldn't it just be 0/1?
No, 1 minus 1. If both of these are the speed of light. Yeah, 1 minus 1, 0. Yeah, 0/0. Mm-hmm. And so it's not as easy to see here. But well, let me keep going here. Because as interesting as that one was, I don't think it gets quite as interesting as the next step. I gave the easy case. The bird was flying horizontal. What if it's flying at an angle? In fact, forget the flying for a moment. What if it is a rod that is leaning forward? Sound familiar? How would you handle that? Yeah, probably the first thing I would do is realize that from one person's observer, let's just say, this rod, it's not a bird, it's a rod. Instead of being straight vertically, it's kind of tilted over like this. But wouldn't it contract along the x-axis? Isn't that what this is saying? But what would happen along the y-axis? It would stay the same, wouldn't it? So, if I had a rod that was tilted, say 45 degrees, then what would happen is it would shrink along the x-axis, but stay the same height on the y-axis. Would it still be 45 degrees? Wouldn't it be a little taller? Taller is the wrong word. Little straighter up? Be less than 45 degrees? And couldn't we calculate that angle? Because we could shrink it along the x-axis and not along the y-axis? That's a homework problem, by the way. You have a rod, it's tilted forward, and it says, okay, if the angle is, and I can't remember what the angle was, I'll just say 45 degrees, but you are asked in the problem to find out what angle does it appear to be tilted now. And it is different. And so we can look at how the position changes, but more than that, we can also look at the velocity. So let's do this same thing again. Let's recalculate this. In fact, maybe I should even put this little equation with this other group of equations. This is saying, how do I get the speed of this? And I didn't put a sub x, but let me do that now. Because I've really said, what is the speed in the x direction? And this is only the x component of the speed. This bird may be moving at an angle. And so I need to look at how does its y velocity compare. And so our first equation was the subtraction of the two, u minus av over a1 minus au c squared. I didn't actually go through the math, but we might as well put it up here. What if it's the other way around? And you can see then that the signs would change here. And so instead of having a u prime, u prime plus the v here, and so the sign would change, and of course the symbol would change. And then likewise down,
That's a U, right? Not a C.
Yeah, thank you.
Yeah,
Yeah, unless the birds still go in the speed of light. But no, in general it's a U, yeah. So it's a U for any speed. And if it's obviously a flashlight, then it becomes a C. And then likewise downstairs, this becomes a plus a V, a U prime over a C squared there. And so I suppose I should confirm that there's a plus sign. Did I even write that one down? I don't think I did. But I think that's there. And so that would be one way of viewing it. So we could take how do I see it from my bike and calculate what you would see, or we could take things that how would you see it from your park bench and what speed would I see. But these, as I said, are really the x components. Let's do this again, but now let's ask about its vertical speed. We already mentioned that in terms of position, there would be a change in the length in the x direction, but not the y, which means that if it's tilted at an angle, we would have a new angle. And likewise for the velocity. If I were to say, what speed do I record? This is me, riding my bike. what do I see for that bird in the vertical? Based upon your information, I can replace the y prime with the y. They're the same. So both of us don't see any difference in terms of vertical distance. And at first you would say, well, so that means the vertical speeds don't change. No. I wish it was that simple. Because what does change? Time does still. And so even though the bird may say only be going in the vertical direction, at which say you would say there's no length contraction in the vertical direction, there still is a time dilation, and time is part of our speed. So the bottom part still comes into play here, where I'm going to have then a gamma down here, and this t prime then becomes a dt, and this one's a minus, right? Minus a v dx over c squared. And like we did last time, if we multiply top and bottom by 1 over dt, in the top we get u sub y. And let me pause right there. See, this is exactly what we would have gotten if we did not have our time dilation, right? You would have said that the speed measured in the y direction by me is the same speed measured in the y direction by you. And this is what we would have gotten before this chapter. We would have just said, look, if you're moving along in the x-axis, that's irrelevant for how much the bird is moving in the y-axis. So both people see it moving the y the same way. However, there is a time dilation, and so this extra factor downstairs is the time dilation. And so the two people do see a different vertical speed, even though the length has not contracted, time has dilated. And so this becomes a 1 minus, and that would be a v, and this one's interesting. What's this? ux c squared. Now, notice I say x because what are we looking for? What component? Y. So the speed in the y direction is affected by the speed in the x direction. Because time is affected by the motion in the x direction. But the length is not. And that one I always find the most interesting. Because first reaction is, wait, there's no length dilation in the y direction. There shouldn't be anything different. And then I realized, oh, yeah, there's time dilation. So, okay, it should be different. Well, then how should it be different? And then when I do it, it comes out with a velocity in the x direction when I'm looking for the velocity in the y direction. But hopefully it makes sense because there should be an x piece down there because the time dilation is based upon the motion in the x direction here. Okay? And so there is the added effect. And like I said, I think that kind of throws me for a loop a little bit. And so maybe I should put this one over here. So velocity in the y direction is gotten by taking the velocity in the y direction as I would have thought, and then the gamma, and then the 1 minus v u x over the c squared. And so there's our bird, or hopefully something more like a spaceship, since a bird's not really going to go close to the speed of light. Well, that's what I wanted to spend the first part, not quite a whole hour, but I think that is another major consequence that just can be a little weird until you kind of think about it. Let's keep going, because like I said, the balance of this chapter is just making some applications of the time dilation to the world around us, realizing that everything we've done had depended upon time. And so all of the equations we have are then readjusted. So, again, going back to our mechanics, you might remember momentum. Yeah.
So if you wanted to do y, is it just the sine curve?
Oh, yeah. So if I can finish this here, uy must be the velocity that the bike rider sees, or I see, and then the gamma, and then the 1 minus, plus now, the v, the u with a prime, and then c squared, like that.
It's a u prime.
Thank you. That's my point, yes. that needs to be an x, because that's part of the time dilation, and that's part of the space motion. So that's the movement through space, that's the effect on time.
The x is the component of the velocity that the observer is traveling.
Yeah, yeah. Fair enough. And I will tell you, and you'll see this when you get your chance this Friday in the workshop. You'll be bugging Don like crazy. Don, which one is the S prime, and which is the S, and which is the S prime? And it's so easy to get those backwards, okay? So as you run through the problems, you'll get more familiar with it. But again, keeping it track, well, there's one observer, that's the unprimed system, and then there's another observer, that's the prime system. And so we can look back and forth at a third event. So that actually helps me. And so as they talk about something happening, remember there's 3 speeds. And keep that in mind. And it wouldn't matter which one you call S or S prime. Keep also that in mind here. But you will need to remember then that one observer has a speed relative to the other observer by v. You want to keep those track. Then those observers see the event happening, so those are the u's. And so there's a u and a u prime. So there's 3 speeds going on there. And it doesn't matter which one you call what. I mean, we could have changed this around. It could have been you, the observer, and the bird, the observer, and now I'm the event. And so you guys can look at my speed and call it a u. The bird can look at me and call it a u prime, and you can look at the bird and call that a v. So this goes either way we want to put it, but we got to keep it straight once we started which object we're going to call the prime system, which we're going to call the unprimed system, and which one we're going to call the event. Once you get that straight, then it's a lot of plug and chug and a lot of algebra.
This is gonna go into more primes if you add more people, but then it just still becomes.
Yeah, but we don't really need to add more primes, because once we know how 2 observers then see an event, if that event is a third observer watching a next event, what we can do is take these 2 and learn something about that event. Then we can just take these 2 and look at that event. So we can do everything from here on out. Observer, 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 event. By eventually just getting to 2 observers and the event. And actually, I'm glad you bring that up. I think there is one like that, where you got to keep straight of spaceship 1, spaceship 2, observer on Earth watches bird. So there's our 4 objects, right? And so we've got to take our 3 and add 1 more to it. All right, well, in what little time we can really spend on this, let's talk about momentum. Didn't we do that back in Physics 121? It was chapter 9. What was our definition of momentum? All right, so we use the symbol P. Good, let's keep doing that. What did we say it was? Well, we said MV, but I have a little problem using V now. Why? I like MU, right. And so let's do MU here. Now, this is kind of a judgment call. I think the U will help you be less confused, but you make the call. I mean, we're used to using v for the velocity of the object, but we kind of changed that in this last example. We use the v for the velocity between the observers, and we use the u for the velocity of the bird here. So if I wanted to know the momentum of the bird, wouldn't I put a u? All right. Except time changes. So are we going to have the same equation? No. And so it was a good first step. That's what we learned first. And as long as you're going less than 10% the speed of light, continue to use that for the equation of the momentum. But let me change it without proof. And your author kind of does the same thing. He says, well, you can go through a conservational transformation, and you can, but for you guys in the short time, and even in the book, he doesn't actually do it. He just says the equation changes. What does it change by? Well, it changes by a factor of gamma. Not a surprise it changes by a factor of gamma, but that's why we will call this then the relativistic momentum. This, you might say, is the more exact equation. Why did we get away with Physics 121 using just mv? Because gamma is close to 1 as long as we're less than 10% the speed of light. So again, what we had done before, what we call Newtonian mechanics, is not wrong, it's just not complete. And so we need an additional factor here to our science.
What mass changes you got here, the speed of light?
Yeah, I'm glad you bring that up, and maybe I'll address it now, but some people will do this. Some people will call this the relativistic mass. And so you still get the old equation. And then they say the mass changes. I think that's a cop-out of trying to make the old equations fit the new ideas. So I don't like to talk about the mass changing. But it's, in this case, it's equivalent, so you can do that. And there's many other cases that it's equivalent, but it does have some problems, and it takes away from really what is going on. So I won't be doing a whole lot of that. Neither will your author. Yeah. Yeah. And so maybe I should point that out, because I think that is taught more in like in a high school level, where they'll say, hey, the mass changes as you get faster and faster. And granted, you can explain things that way, but I think it's best if we just say there's something different going on, and the mass doesn't change. There's an extra factor of gamma. You'll see that happen again when we get to energy and stuff. Yeah, yeah. Now, with that said, let me take you back to Physics 121. How do we get kinetic energy? Okay, how do we get there? It did come out to be 1/2 mv squared. We did an integral. Something like this. We said, look, if you took the net force, right, and you integrate it from some initial position to some final position, and we put for net force ma. Actually, let me go back even one step before that. We actually put dp dt dx, which then led to m dv dt dx, which then led to putting the dx with the dt, which gave us a v dv, which then led to 1/2 mv squared. Yay, right? And so that's where it came from, and just in case you forgot, chapter 7 was a while ago. But that is using mv or mu for momentum. Is that even correct? Not quite. So, shall we go back and redo it? Shall we find the new formula for kinetic energy? Shall we realize that this is not the complete answer? It's not the complete answer because it did not use the complete equation for momentum. So we should have a new equation for kinetic energy also. What should it be? Well, I guess it should be the integral of dp dt dx. The thing that's different, dramatically different, is that I don't just have a v, I have a gamma. And a gamma has a v in it also. So this would be a derivative. Oh, and I said I was going to use u. And it looks like I defaulted back to v because I was going back to here. Is that okay? I'll leave it as a v there. But as we continue on for the new formula, let me use the u. But this would be then an mu over a square root of 1 minus u squared over c squared dx. And isn't that going to involve a u sub? An x sub. And I'm going to save a little time and cheat here. Well, maybe I'll write down an intermediate step. It looks like right here I actually took the derivative. Should be a product in here. And then it simplifies. So, yeah.
You can go straight to the answer.
All right, straight to the answer. Okay, so, but if you got more time, take the derivative. You'll get two terms. Put those terms together, they'll be like terms. Then it's actually not a hard integral to do. And that's what Einstein noticed. And here's what he came up with when he did all that. He came up with this idea that you would get a mc squared over the square root of 1 minus u squared over c squared minus mc squared. Which you might recognize this as our gamma factor, not a surprise. After we first take the derivative of it and then integrate it, we get back to the same power. We like to write it then as gamma mc squared minus mc squared, which is gamma minus 1 mc squared. And so there's our kinetic energy. And so maybe I'll put a box around it because I think of all of our formulas that we have modified, that one looks the least like the one we had before. I mean, at least our momentum one probably looks the closest. Our momentum was just an m and a v or a u, and then we just multiplied by gamma. Our position ones changed by an extra factor of gamma. Our velocity ones changed by an extra piece in the denominator, but at least I could see the old piece of it and then something modified to it. That really doesn't look like it here, does it? But rest assured, it is. It just doesn't look like it. But I'll start with, this is our new formula. So, if somebody asked you to calculate the kinetic energy, as long as you're going less than 10% the speed of light, use Newton's laws. It's a lot easier than that crazy equation, and it works pretty accurate. But once we be more than 10% the speed of light, that is getting too far off, and we need to get to the more complete equation for the kinetic energy. Yes?
So does it mean the energy is not conservative anymore in the high speed?
No, energy is still conserved. Yep. We just would be using this. And so if we had a problem, instead of like me dropping a ball on the earth, we would say the potential energy it starts with is equal to the kinetic energy it ends with. And where up here I would use mgy, and down here I would use 1/2 mv squared. If instead this was like a black hole, I would say, okay, if I drop the ball from someplace up above the black hole, I would drop it, I would calculate its potential energy it starts with, then I would set it equal to its kinetic energy, and I would use this one if it is going really fast. If I didn't use this one, I use this one, then I might actually get a number that would be greater than the speed of light. And that's not going to happen, because this one allows it to go greater than the speed of light. Does this one? And that's kind of the first thing I want to discuss here. Let's look closely at this equation. There's a couple things I want you to see, 3 in particular. Yeah.
So if you were given, if you were already given kinetic energy in the problem to solve off Maxwell's points, but you're assuming that you're going super duper fast, and you want to use that equation, would you be able to solve for velocity?
Oh, the best thing, well, okay. Are you asking if you, when to decide to use this one or this one? Or are you just...
No, just if you already know you're supposed to use the new one,
okay,
and you were given k, and they asked you to solve for how fast is the object going,
right,
you would solve for gamma?
Yeah, solve for gamma, and then gamma is inside there. So it takes more steps, yes, but that's the key. Just remember, gamma is buried inside of it is a v. So we find gamma first. Once we find gamma, then we can find v. Exactly. Now, you didn't quite ask this question, but this is a good one. You always kind of wonder, should I use this equation or this equation? And if you already knew you had to use that one, then okay, fine, solve for gamma. But what I like to do is maybe start with this one and do a calculation. And if this one, because it always comes out too high with this one, and if this one comes out to be more than 10% the speed of light, then I should have been using that one.
Well, shouldn't that be the most accurate one?
Well, yes, this would be the most accurate one. So if you want to just say, I'm going to always use this, fine. But to be quite honest, when you get to cars and boats and planes, it's just a lot of extra unnecessary work to get to the speed, because you would get the same speed except within the 10th decimal place. So I would encourage you to continue to use this. I don't want to leave the course feeling like everything you've done you're going to throw away and you got to start all over again. Continue to use everything you have. Just remember that it is incomplete, and there will be times where you might want to make the next step up and look at the new formula for, in this case, kinetic energy. But it could be the new formula for velocities. It could be the new formula for momentum, whatever the case is. So this is that new formula. Let's look closely at it, because one of the things that was kind of implied as we went along is, can this bird or spaceship ever go faster than the speed of light? Can it ever even get to the speed of light? And I would say no. Why? What do we say about gamma? If I were to plot gamma versus speed, didn't we say it starts about 1 and then does what? Doesn't it get larger and larger and larger and larger and larger? So, as we get closer and closer and closer to the speed of light, how much energy does it take? A lot, right? I mean, if I were to actually if I could get to the speed of light, how much energy would it take to get to the speed of light? An infinite. Then there's our answer. That's why we say, we're not going to get to the speed of light. We can get closer and closer. You can put more and more energy in, but unless you have an infinite amount of energy, you can't get to the speed of light, let alone going beyond the speed of light. That's not what this equation says, right? This equation says, hey, put in the speed of light, albeit a big number and albeit a lot of energy. It's not an infinite amount of energy. And this equation would imply that you could get to the speed of light and beyond. But the first thing I want you to see is this one makes it very clear. You cannot get to the speed of light. You start getting more and more energy. You pump more and more energy into this. You have a rocket that's got this infinite amount of energy on it. it goes faster and faster and faster and faster, and it gets closer and closer and closer to the speed of light. Eventually, maybe it's going 99% the speed of light, then 99.9% the speed of light, then 99.99% the speed of light. But the amount of energy to go from 99.9 to 99.99 the speed of light is a lot of energy. Probably far more energy than it took just to get to 99% the speed of light. That last 0.1% is an enormous amount of energy. And then to get to 99.999% the speed of light is even more energy.
That's talking about doing that in space.
Sure, space, why not?
That's strange. Think about that.
What's strange about it?
Because it's space, there's no other interference. So the more energy you put in, the more output you should be getting.
The more energy you should get. And I'm not saying you're not getting more energy. You're just not going faster.
But it's so small.
So why does that bother you?
Because it just doesn't.
Because you're still thinking F equals ma. Exactly. And so F does not equal ma.
What's the fastest you've gotten to?
The fastest I've gotten to? I've gotten, I do not know. I know that some of these subparticles will be 99 point and at least 5 more nines to the spin of light. Their objects are small, electrons and other exotic stuff, even protons. But these atom smashers, we often say, hey, we get them to the speed. Sometimes they'll say even we get them to the speed of light. That's kind of just meaning we got them to 99.99999% the speed of light. But I don't know how many nines it goes, but I'm quite sure I have seen 99 and at least 5 more nines to the speed of light, yeah.
But when we turn on a light, aren't we creating photons that are going the speed of light because they're a light?
Oh, okay, fair enough. Maybe I should have clarified this a little bit better. This is the kinetic energy of an object with mass.
Okay, and we consider photons segments.
Right, and I'm glad you bring that up because this is the next part of this discussion. There's a bunch of interesting things in here, and I should have clarified that this equation really says we can get close to the speed of light, but never the speed of light for anything that has mass. But if it doesn't have mass, then we are looking at infinity times 0, and that could be a finite number. Right? And we're back to our calculus and our limits here. And so things like photons and any other objects, which I'll just say photons for now, if they have no mass, they certainly can go the speed of light. In fact, they can only go the speed of light. Because if they were less than the speed of light, they would have no energy. So the only option we have is less than the speed of light for things that have mass, and things that have no mass only go the speed of light. That's what that equation is saying. Okay. Well, like I said, there's just some really bizarre stuff in here that is good that, get exposed to, although only some of you will go and beyond and actually use this in designs or understanding the physical world. But all of you, as part of your education, should be exposed to it. So someday you'll be having coffee, having conversations, and saying, "Yeah, I remember those relativistic effects," and I'm glad we don't have to do that for what we're designing here today. But I remember having those discussions in college. So that is point number 1. Point number 2, though, it's probably worth seeing that these really are the same looking equations. I know it doesn't look like it, but let's do this. Let's go and look at the function 1 minus x raised to a power of n. Let me call this just f of x for a moment. You might remember, oh good, somebody said it, Taylor series, right? I can say that any function can be expanded in terms of the integer n going from 0 to infinity, expanded around some point a where I take the derivative, evaluate it at a, and over n factorial. So let's say I do this for this function. Let's set A equaling 0 for simplicity, because what's nice about it is when I set A equaling 0 here, I will get x minus 0, which is, 1 minus 0, which is 1, raised to any power is still 1. And so this becomes, I guess I'm going to have to think about it. 0. Raised to a 0 power is 1. No, I guess I messed up there. It's the nth derivative, isn't it? How do we write that? Nth? Trying to think of how you, do they do n of the function evaluated A? Maybe like that?
I think it's like
F to the n, or F derivative to the n. But either, whatever the notation that you're used to, that's what's meant. You take the nth derivative and then you evaluate it at A. So if I do that for the first one, this becomes 1 here, that becomes a 1, and that becomes a 1. So there's my first one. If I take the first derivative of this, boy, what do I get for the first derivative? The first derivative is what? N, 1 minus x, n minus 1, with a chain rule, right? So when I evaluate it, I am going to get a 1 to the 1 power, that's a 1. I'm going to get the first derivative evaluated at 0, that's a 1. So that's a minus an n, 1. Oh, that's an x to the n. There we go. Plus the next derivative. And that's probably enough to see what we want to see. If I take the derivative yet again, I guess I get an n and an n minus 1. When I take this down, it would be 1 minus 0, that's 1. This would be an n minus 2, of course, but that's still a 1. This would be x squared, and this would be over 2 factorials, just 2. 2 minus blah, 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 blah. Now, why do I say all that? Well, what if x is a small number? What if x is much less than 1? Well, see how we're raising it to higher and higher powers? And if you have a number less than 1 and you raise it to a high power, doesn't they just get smaller and smaller? All right, so something that looks like this can be approximated with just a few couple of terms because each additional term is smaller and smaller. So let's look at gamma for a moment. Gamma can actually be written in this way. We can write it as 1 minus v squared over c squared raised to a negative 1/2 power. And so if we think of n as equaling negative 1/2 and x as equaling v squared over c squared, isn't that what I have? Question. Oh. Oh, yeah. Should I go back to use? Okay. I put v there, didn't I? And I'll, since I got started, I'll keep it with the v's here. No, I got use here. Ah, crap. All right. So I'm going to have to do use. U. Okay. Yeah, my sloppy writing, they look the same, huh? All right. So, okay. But the point here is, let's take a close look at this. That if I write down the kinetic energy then, here's my mc squared. Let's look what I have. I can replace this function gamma with 1. Let's see if I got this right. A minus an n. Now an n is a negative 1/2. And then x squared, which is u squared over c squared. Then I can go plus, then I've got an n again. That's a negative 1/2. And that's a negative 1/2 minus 1. This would then be u to the 4th over c to the 4th. That'd be my x squared over 2. I didn't give myself quite enough room. There would be more terms, but then I need the minus 1. So that's what gamma is, and don't forget to subtract 1. So minus 1 here. Because that 1 and that negative 1 cancel off. The negative and the negative make a positive. Notice I've got a c squared with a c squared. And I'm going to get a 1/2 mu squared. Anybody excited like me? And so what I'm trying to point out here is this equation for kinetic energy is really partly this plus other things. And so what Newton really discovered here is the first term. It took Einstein to discover all the other terms, right? And so that's why I would say that this equation really is this equation if you are looking at slow speeds. Because the next term, look at it. The next term would be, well, that's a 1/2. That's a 3/2, and that's a half of that. So that's a 3/8. And a negative make a positive. So that's 3/8. There's the m. This would be speed to the 4th power over speed of light squared. And so if you wanted to improve by one step Newton's equation for kinetic energy, and I shouldn't say Newton, Newton's comes from Newton's laws, the 1/2 mv squared, then this would be your added factor. It's why some chemistry books, and I'm not sure any of the beginning chemistry books, but maybe some of the last chapters, you guys in chemistry, I've seen chemistry books, and I've had students who come and they'll look at the electron going around the atom. Now the electron going around the atom doesn't go quite at 10% the speed of light, but it does go about 1 or 2 or 3% the speed of light. So it's really fast. And so I have seen chemistry books that say, hey, let's calculate the kinetic energy of the electron. And they have this plus this. And then students always come and go, I've seen this, but why are they doing this? And well, that's the next added term. It's probably not that sufficient until you start getting up to 2, 3, 4% the speed of light, but they wanted it more accurate for the kinetic energy, so they gave a more accurate, although not complete, formula for the kinetic energy. And so this is point number 2, that this one does look like that one. And point number 3, probably the best of all, is a whole new discovery here. Something that never even dawned on Einstein or anybody before him, but can't be ignored as you look closely at that equation. And that is, let's rearrange it. Let's do the distributive property and put the negative on the other side. So here is kinetic energy. Take that negative mc squared over here and put it on that side of the equation. And on the other side of the equation, let's put the gamma. That begins to look like something. doesn't it begin to look like a summation of total energy? I mean, didn't we do a lot of kinetic energy plus potential energy equals total energy? And so if we call this total energy, we see that an object is made up of not just its kinetic energy, but its... What's that? That's a new form of energy, one that hadn't really come up for discussion before. We like to call it its mass energy. You are probably familiar with one of the most famous equations of all times, and nobody seems to really know where it comes from, except for you educated people. E equals mc squared. What does it mean? What does the m mean? Mass. What does the c mean? What does E mean? Energy. What this is trying to say, and what this is the first question or hint in history is mass just kind of some kind of form of potential energy? Is it stored there, kind of like a potential energy? If I had a rock on a hill, that big boulder sitting up there, it has potential energy. Now I'm not saying it's going to fall, but if it did fall, what would happen? We would lose potential energy and gain kinetic energy. We would convert it from one form of energy into another form. And so the first time brings up this question, is that what mass is? Is mass a potential energy? That if we could somehow get rid of the mass, it would show up as energy? And that's what I'm about to show you. Yes. Mass, despite what you might have heard in your chemistry class or your high school physics, is not conserved. Mass can get lost and go where? Into energy. And so we like to say we don't have conservation of mass. You might even say we don't have conservation of energy. We have conservation of mass energy. So we don't have space and time, we have space-time. We don't have conservation of mass and energy, we have conservation of mass energy. And so mass is a type of form. Let me start on the little scale. I'll start on the little scale, and I even wrote down some numbers here. But when this comes up, this brings up the whole issue of atomic energy. Something that was never even thought of before, but the early scientists knew this much. That if you take, where did I write down my numbers? A proton and you weigh it. And so I'll take a little tiny proton, which is essentially the nucleus of helium, if you're not familiar with your chemistry, and you weigh it, it has a mass of 1.007825 atomic mass units. Well, if you're not familiar with atomic mass units, it is a small amount of mass that is used to measure small little things. So that's why we like to measure little protons and neutrons and electrons in atomic mass units. So that's what you get when you measure one proton. You can do the same thing, and I'll make a circle and leave it open, with a neutron. If you take one little neutron and you weigh it, you get 1.008665 atomic mass units. So, what is helium? What is in the nucleus of helium? Do you guys know? There's 2 protons and 2 neutrons. So, let's take the nucleus of helium and weigh it. I'll represent it in a picture with 2 protons and 2 neutrons. and weigh it. If you carefully weigh it, you come out with 4.00262 atomic mass units. Now let's look closely. Does this equal 2 protons? Plus 2 neutrons? Isn't that bigger than this? So when you take 2 protons and 2 neutrons, you put it together, you make helium, the result you get is less mass. Was mass conserved? No. Where'd it go? Energy. This is what we call nuclear fusion. The energy has been converted from what we would call a mass energy into usually a heat energy is the result if we don't really know how much more to control it. Although I guess originally it probably comes together and it's kinetic energy, and then that kinetic energy on a molecular level is heat energy. And so things get really, really hot here. And so this is that new and important idea as we come to the end of this chapter, that there would be a release of energy. Delta E would equal to delta mc squared. But here's probably the most interesting thing of all. Notice the c squared. Big number or small number? Big, huge number. What does that mean? A small amount of mass can result, or a loss of a small amount of mass can result in an enormous amount of energy. Or the other way around, an enormous amount of energy can be the equivalent of a small amount of mass. If you're familiar with a nuclear aircraft carrier, the reason it's called nuclear is where does it get its energy? A nuclear reactor. What that reactor is doing is, through clever design, now not this design, but through clever design, is changing mass into heat. Once you get heat, you boil water. When you boil water, you get steam. You put steam under pressure, you turn a turbine, and you move your aircraft around. You move turbines and make electricity, which then runs the rest of the ship. And so this entire ship, for 50 years, runs on a golf ball. There's the energy. Although, in order to control that energy, we got a lot of other stuff and equipment with it. But the raw energy itself is really pretty small. In fact, I want to do a quick calculation. I thought this would be a good way to do it. If you do this, you will find out that delta M is 0.03037 atomic mass units. That's the equivalent of 5.04 times 10 to the negative 27 kilograms. Okay, so one little set, four particles, 2 protons, 2 neutrons, coming together certainly does not lose much mass, and therefore doesn't produce much energy. If you go to calculate the energy this comes out to be, it still only comes out to be 4.53 times 10 to the minus 12 joules. So it doesn't sound like much energy, and agreed, it's not much by itself. But again, that's only one atom. Remember we said if you took something that was as big as a dust particle, it would have more atoms than there are stars in the universe. So although this isn't much per each individual one, if we can make a small piece of dust change into this, this can be an enormous amount of energy. And that's the idea of nuclear energy. That's the idea of what, in this case, we would call nuclear fusion. These come together. There is a loss of mass. We no longer have the phrase conservation of mass. We have conservation of mass energy. We have creatively converted mass into energy. This can be, like I said, an enormous amount. If you guys ever see the old, what's the old Star Trek TV series from the 60s, right? Beam Me Up, Scotty. What's the science behind that science fiction? Yeah, it's right here. If you could take a machine and change all your mass into energy, well then, it's possible. Better still, if this energy was in the form of an electromagnetic wave, couldn't you then take all this energy and beam it to another place? Convert all that energy back into mass, and now you have reassembled the person. And so you go from a person to energy to new location at the speed of light. And that's the science, if you will, behind the science fiction. Although, if you calculate all of this energy, I think it would be enough energy to blow up the planet. So you're going to have to be really careful with how much energy is there. And so just to give you an idea, I looked up some numbers out of curiosity here. I said, I wonder how much energy, say, the United States uses in 1 year. Now, this was a few years back, but as I looked up the total amount of energy, it came out to be 25,150 terawatt hours. And maybe we should talk about that unit because it may not be as common to you, but this is a lot of energy, as you might suspect. 25,100. What's tera? 10 to the 12th. What's watt? Joules per second. What's an hour? 3,600 seconds. So let's go ahead and do a quick conversion here to how much energy would the entire United States, me, you, and everybody, all, what, 350 million of us? Or is it that many? 300?
I think it was 301 the last.
380?
Yeah, like 380.
380? Oh, man. Oh, we need to kill some of you guys off. This is way too many young people here. All right. yeah, because I thought it was like 350 a while back, so 380 makes sense. Okay, so if I put that number in here, 25,155.
313 is the last.
You think it's 313?
It is.
Oh, then we don't have to kill any of you. Good. It's only 330. There's still enough food and water. I don't know about water in California this year, anyways. We're all going to have to take a vacation trip to Colorado, I guess, and come back with water. That's the requirement now to live in California. You got to bring your own water. Pack it in, pack it out. Type thing. All right, but 25,155 tera, 3,600 comes out to be, as no surprise, 9.05 times 10 to the 19 joules of energy. Quite a bit of energy, fair enough. But what if we got all of that energy from mass?
Can you convert any energy into mass though?
Well, it's theoretically possible. Can it be done? No, not on a well-controlled scale. You see, if I really wanted to get a lot of energy of this, it would be great if I can convert all of this mass into energy. But this is the best what today's technology can do, is take advantage of what nature already does on its own and fuses together 2 protons and 2 neutrons and releases a lot of the energy. And so this is, like I said, not our nuclear reactors, but this is what's going on in the sun. Maybe I should point that out. The sun does this. In fact, maybe we should do a calculation for the sun in just a second when we're done here with the United States. But here is the United States. And if I set this equal to mass and go energy divided by c squared, what do I get? 3 times 10 to the 8th squared. And I come up with only 1,000 kilograms.
Wow.
See this desk right here? 1 meter by 1 meter by 1 meter? If this was filled with water, that'd be 1,000 kilograms. So there is enough energy in this desk to run the whole country for 1 year. And so the amount of energy stored in mass is an amazing amount of potential energy. We still have yet to figure out how to harness it out safely.
Also includes mass with the proton and neutron.
Yeah, but what if I got rid of all those?
Have you heard the antimatter?
Exactly. So if I could take 500 kilograms of matter and 500 kilograms of antimatter and merge them together, I'd get no mass. All of it would be converted to energy, and that'd be enough to run the country for a year. Right? And so obviously a lot of this is way off into the future, but there's an enormous amount of energy locked up in the form of mass energy. And we're just beginning to learn to touch the surface of it. This is what the sun is doing. In fact, this was a big problem in science for a long time because many scientists before 1900 thought, where does all that energy from the sun come from? Is it just like a flame where you turn hydrogen with oxygen and make water? Well, if you run through the numbers, there's not enough energy there. There is no way the sun can be burning like a flame, like burning hydrogen. There's just too much energy. And so what was discovered in this is the process. This is what is happening in the center of the sun. We have nuclear fusion, and we are hooking them together. Some rough numbers may be something like this. Here's the sun. I know that the sunlight goes out to the earth, and I know that the intensity is about 1,300 watts per square meter by the time it gets to earth. All right. So the intensity, which is power over area, power then would be intensity times area. The intensity is about 1,300 watts per square meter at the earth, but the light from the sun goes in all directions. It doesn't go just towards the earth. So that energy from the sun is spread out on a surface that is 4 pi r squared, r being the distance to the sun. And so here's a rough calculation of how much power is coming from our sun. So 1,300 at the earth, then times 4, then times pi, then times 1.5 times 10 to the 11th squared. And so the energy coming from the sun is, that's per second. This is how much the United States uses per year. So solar power is a pretty good place to go. There is plenty of solar power. We're probably more acquainted with getting the capturing and use of solar power than we are of nuclear power, but we should probably pursue all of our options here and seeing which way we should go in getting energy. Because I should have pointed out, although we can't do it yet, even if all you did was convert hydrogen into helium, there's nothing dangerous about that. It's the fact that we can't quite control this yet, and so we use things like uranium and plutonium and stuff that does have radioactivity and long lives here. Anyways, this is the power from the sun. So this would be how many joules per second, watts here. If I converted that into mass, I could take the energy, or maybe I should say power, and divide it by c squared. And so the mass per second that is being converted in our sun, divided by 3 times 10 to the 8th squared, is 4.08 times 10 to the, oh, why did my calculator do that to me? How many significant? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. And so 4 billion kilograms a second is how much mass our sun is gobbling up every second, converting it. So again, don't let anybody tell you mass is conserved.
Just through this reaction, right?
Oh, now, fair enough. That is all happening through this reaction. So how much mass is involved is much greater than that, but that's the stuff that is lost. You lose this much for every reaction. So we could figure out how many of these take place. I guess it would be the ratio of that, 27 to 29. So 27 plus 29 is 36. So about 10 to the 36 atoms come together every second in the center of our sun. Well, maybe I spent too much time here, but I think that is an amazing piece of this whole thing, of that mass can be converted into energy. And so we introduce a very important concept. We get away from conservation of mass and say conservation of mass energy. Or sometimes we just say energy, but what we mean by that is mass now is a form of stored energy, and it can be converted one to another. Let me keep going, especially in the short amount of time we have left here, and show you just 2 more things real quickly, and then we'll be done with the chapter and ready to move on to the other part of this, which I guess we won't get a chance here today here. But you might remember that equation that I've been working with, kinetic energy plus mc squared equals to total energy now. Is it still there? No, we kind of lost it here. Let's do this. Let's square both sides. Now on the right-hand side, that obviously becomes e squared. Again, I'll save a bunch of algebra here, but this comes out to be, and I think you can see how you're going to get an mc squared, but there should be 4 terms here. And so if you worked out those 4 terms and reduced them, you get this. P's momentum. And so this is your gamma mu that we worked out before there. But here's why I bring that up. This also brings up something I think quite surprising. What if I had something with no mass? Don't I get this? And so these little photons we were talking about, no mass, that means they go the speed of light. Do they have momentum? Wait, they're massless. Do they have momentum? You might remember we brought this up. Is it possible to get momentum here? Yeah. Even if the mass is 0? Yeah. How? You have to go the speed of light. So, if I have a massless object, which can only go the speed of light, could it also have momentum? And the amount of momentum would be the energy it has divided by c. And if we go back to our optics chapter, we learned that one of these little photons had an energy of hf. Which then, if we also remember the speed of light divided by the frequency is the wavelength, we can say that our light, and I think this is a bit surprising it's the first time you come across it, has momentum. That means if I'm standing in a room and somebody turns on the light and the light comes down, ow, 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 ow. I just got hit with photons. Not only that, they have momentum. Now, fortunately, how much momentum do they have? It's divided by c. It's just the opposite of our energy issue. You see, our energy issue was multiplied by c squared. And so a little bit of mass made an enormous amount of energy. What are you saying here? The momentum, even with a lot of energy, has what? Well, of course it has speed of light. But it really has very little momentum. And I'm sure that's why all of you are thinking, I have walked into a room where the lights are turned on, and it did not knock me over or push me away. Fair enough, because the momentum is small. But they do have momentum. And if we were real clever with this, perhaps we could launch something into outer space. Not by putting a rocket on it, but what if we just go out in outer space and make a mirror? A big mirror, perhaps. Maybe a kilometer by a kilometer. And we point the mirror at the sun. So what happens when the photons hit the mirror? Bounce off. Push. And we have a solar cell. We can then go sailing through outer space by using the impact of the photons instead of our sailboats, where we would use the impact of the momentum of the wind. And so these photons do have momentum. And that's going to come back in the next chapter. And one last thing as we get into here, which those of you who've gone through 122 will appreciate this maybe a little bit more. For the rest of you, I'll ask you to keep this in your memory bank until the last lecture of Physics 122. But if I were to take a wire and a second wire and just set them side by side, I would have a bunch of positives in here and an equal number of a bunch of negatives. Fair enough? That's what we mean by a wire filled with copper. Equal number of protons, equal number of electrons. If I had a second identical wire, I would do this. And if I just laid them side by side, nothing else, most of you would probably look at this and say, well, there's no interaction between them. It is a bit more complicated than that. I would say this happens. Let's take a look at this wire here. How do these electrons respond to those protons? They get attracted. Let me call this F minus plus. The minus is here, the plus is here. How would the minuses here respond to the minuses there? Push away. Let me call that F minus minus. How would the positives here respond to the positives here? They would repel. Let me call that F plus plus. How would the pluses here respond to the minuses there? F plus minus. And as you look carefully at this, I would say, well, since I have equal numbers of pluses and minuses, I have equal densities throughout, these forces are the same, these forces are the same, what would I get for the net force? 0. Okay. But what if I made some electrical current? And for those of you who haven't gone through 122 yet, electrical current is when you have charges that are moving. And the way it works is the electrons move. So let me have the electrons here moving. Let me have the electrons moving there. Let me stay in my red pen for a moment. As these electrons look at these positives, what are they going to see? Well, I guess these electrons are actually moving down, which from their perspective would mean the positives are moving up. And if they're moving, what would happen to the spacing between them? Wouldn't they get closer together? So this wire, these electrons, look at those positive charges and think they're closer together. If they're closer together, it thinks there's more of them. And so what would happen to this force? Would it stay the same size? It would increase a little bit. So let me put in red a little increase. How about this one over here, where these electrons look at these electrons? Yeah, it would be like they're not even moving, right? So they would see everything exactly they saw before. So I'm just going to leave that one alone. You would get the same repulsive force. How about this one? These protons look at those protons. Not moving, same thing. But what about these protons as they look at those electrons? They see them moving. Length contraction means they look closer together. It sees more of them, so what happens to this force? So it increases. So I would say that these two wires, because of length contraction, have now changed their electrical force and they pull together. But what if you knew nothing about length contraction? What would you say? You would say there's some new force. Let's call it magnetism. And that is what magnetism is. Magnetism, as those of you who had for 122, will realize that it was a good approximation. It's not wrong. Don't forget all the equations we learned about magnetism. It's very useful. But it's not complete. It's not really what is happening. It is a lack of humans' understanding about length contraction. So, there is no such thing as space-time. Or space and time, it's space-time. There is no such thing as conservation of mass, it is mass energy. And there's no such thing as magnetic fields. We like to call it electromagnetic fields. It is length contraction.